Hi, my name is Brenner. This past summer, I had the opportunity to intern at Astronomy, the education branch of Max Planck for astronomy. I had this opportunity as a John Ernst Foundation Fellow, as a participant of the International Summer Science School Heidelberg. In my project, I partnered with Jack, a fellow John Ernst Foundation Fellow, and Mihi, a German who had an internship at Haus der Astronomie. Our mission was to determine the distance from the Earth to the Sun using the Doppler effect for light. And so we started with getting familiar with our equipment. We had a telescope and a spectrograph with the camera, as well as a handful of new computer programs that no one had ever used before. So we started by taking images using the spectrograph of sodium and krypton bulbs in order to get some control images that we could later compare the Sun images with. Once we took the images, and finally had good weather, we took a measurement of the Sun. And then during week 2, we spent most of our time trying to compare our information from the Sun with our control images. And in addition, we were comparing the information from the Sun with a solar atlas that was taken by professional astronomers. And this was difficult because the solar atlas had much greater detail than what our equipment was able to provide, and we were trying to match our solar atlas with our wavelengths in order to see what precise wavelength we had photographed in our measurements. During week 3, we actually ended up remeasuring. With all of our experience behind us, we were able to take our measurements and get precisely what we were looking for. And then we worked quickly to try and process all those images and get some conclusions by the time our time was up. So the Doppler effect is the change in wavelength for the observer who is moving relative to the origin of the wave source. So in that image, you can see as the wave comes closer to you, it will become higher pitch. That is just like when an ambulance is driving by you and it approaches you and you hear the pitch change. So we were taking our measurements through spectroscopy, which is, interestingly, since we were in Heidelberg, Dr. Bunsen, a chemist, essentially invented spectroscopy in Heidelberg. But spectroscopy is a way where you can measure the individual wavelengths that are emitted from a certain element, which is how astronomers know if a certain element is on a certain planet, and we were going to use it to determine the change in the wavelength as we measured around the Sun to try and find the poles and the equator, because at the poles there would be no redshift or blue shift, and at the equator there would be maximum redshift and blue shift. Here's the geometry of our mission, and as you can see along the equator, the velocity is the maximum, and that results in the highest and largest redshift and blue shift. And at the poles, it is 0 because there was no redshift and blue shift. Once we found the equator, we would find the radius, and then using trig, we would use an equation to try and find the distance from the Earth to the Sun. So here's a picture of taking measurements, and as you can see, we focused the Sun in on that inner circle, and then I would measure the in between the little hole that you can see in between the inner and outer circles, and along that are 24 equally spaced marks. And in between each rim measurement, we would take a center measurement to adjust for the natural movement of the Sun. And we went all the way around, and here you can see Miki was taking the photos and Jack was taking any notes that were pertinent to each photo. And then you can see the apparatus in more detail when we had it set up inside as part of our calibration efforts. I believe we were setting up there to take photos again of a krypton bulb. Here were some of the images. The green line is an image we got from the sun, and the two yellow dots are an image we got from the sodium bulb. So the image from the sun was an unknown wavelength at the time, and we were trying to determine exactly what wavelength it was, and we were doing so with those two sodium dots. So most of our time was spent processing our images, and this was the most difficult part. And we had to go through each of our images methodically in order to see if there were any differences and graph the various wavelengths. And from there, we could ultimately match it with the rotation of the sun. My favorite part of the internship was when we got to go over to Max Planck Institute for Astronomy and hear the talks that the scientists gave. I really enjoyed hearing the talks because although they were over my head, I could tell by being in that room my game was raised by having those thinkers and those awe-inspiring scientists around me. My personal favorite talk was given by David Hogg, who is in the picture, and he talked about machine learning. With the advent of machine learning, there are kind of two camps of astronomers. One camp believes that machine learning is the best thing that ever happened and it will solve all their problems. And the other believes that machine learning won't really change anything or won't be helpful at all. And David Hogg was kind of presenting a middle road. Prior to this talk, I didn't know much about machine learning, and I found it very interesting to learn about it. So our outcome, we did not determine the distance from the Earth to the Sun, but we were able to determine that the Sun is rotating, which, as our mentor Marcus says, is highly untrivial. And here you can see the wavelength that we got from an image that essentially had a green line similar to the one I showed you previously. And from there we were able to find a line of best fit from a sine curve, and then overlay the rotation of the sun to it. And from there we could match them and determine that it was rotating. And I want to thank all the people who made this internship possible, as well as you for reviewing my scholarship and considering me. So thank you very much and have a great day.